Okay, so it's recording now. So big picture, what we're going to do tonight is kind of the theory of derivatives, but they don't teach you how to take derivatives, so it's a lot of theory. And in our textbook, they never teach us how to take derivatives. So next week, I'm going to actually do the derivative rules, and we'll practice doing that, and we'll do a lot more with limits as well. So this is just kind of the introduction to it. So let me just put this up, and then so today, the new problem set's posted. That's due next class, and your journal reflections due next class as well. So I put spots for both of those up on the our program so that you can see it. So let me get my iPad going. So I'm going to share this. Okay, so that's going over, which is great. We can unplug this. Okay, so then we are in here. So these are the notes that I posted. So we start out saying, how do you measure speed? So what they don't tell you initially is that speed is just like velocity. So this is velocity. So we're going to be measuring it in miles per hour. And so if you're given this example, if someone tells you that this guy Schumacher, he traveled a 0.25 of a mile in 4.446 seconds. In 2005, his record-breaking speed was 337.58 miles per hour. Is this correct? So you're going to use dimensional analysis to figure out the actual answer. So dimensional analysis looks like this. So if this is miles and the time was 4.446 seconds, and you want to go to miles per hour, you're going to convert seconds initially into minutes. And I should say this is miles. And then you're going to say minutes can go into hours. And you'll actually get 202.4 miles per hour. So that is incorrect. So just, I don't know why they threw in dimensional analysis at the beginning, but they did. I think it was just to express exactly what velocity is. So then they give you these equations, or these graphs, I should say. So if you know that velocity is just the change in distance over the change in time, then it's just slope. And so if you look at the first one, you can see the slope is clearly 0, right? So this slope would be 0. And if you think of that about it, he is traveling, but he's not moving at all. There's no time's going on. So time's traveling, time is going on, but he's not moving. So therefore he's sitting there at 0 velocity. So slope is 0, so therefore velocity is also 0. This one, you have a constant increase. So there's a constant slope. So say it was 10. So then you would have a constant velocity. It's not changing. It's always going to be the same. As opposed to the bottom two, here you would be having increasing velocity. And here you'd be having decreasing velocity. So again, a lot of big picture. So velocity is the slope of the position graph, and we talk a lot about position graphs in this section. So they didn't really talk about average velocity versus instantaneous velocity. So what we've been talking about here is more the average velocity, because that's going to be your slope of a line. We're going to get to instantaneous velocity, and that's the whole calculus piece of it. And that's when you're going to take the limit so that you're taking a slope of a line, but it's not quite the same line. So looking ahead, this line will be the secant line for the average, and this line would be the tangent line. And that's going to be the calculus line that we're going to look at. So we're going to do a little bit of limits like this, and then next class we'll go into the rules. But they're still kind of doing just big picture things here. So they're keeping with the velocity idea, and they're saying if they have a car that's traveling in a straight line, and so it has straight line accelerate uniformly between 2 and 9. So if we divide this up so that this is kind of one piece here, this is another piece. So you have 3 distinct groupings.
Mhm.
So what's happening initially is you have a constant velocity. Excuse me, your velocity is changing. This is a velocity curve. So this is velocity over here. It's not distance. So if you can figure out your average velocity, so to figure out what's going on here, because I want to figure out what distance I travel each time. So if you figure out your average velocity, and you can say, okay, well, let's see what I would do. I could just take the average of these 2 velocities. So that would be 9 plus 2 divided by 2, which is going to give me 5.5. And so this is going to be meters per second. So that's my average velocity. How far did I go during that window of time in that block 1? So what would you do? Take that and do what with it? If this is time down here, couldn't you figure out, okay, well, I traveled that way at that average velocity for 10 seconds.
Mhm.
So I'm thinking that I'm traveling 55 meters during that window. Does that make sense?
Yeah.
And then go to the second one. And I picked up a cold, so I am sucking on cough drop. Drinking water. So the second one, it's a flat curve, so that means that the velocity is always constant.
Mhm.
And so that makes it easier because the velocity is just 9 meters per second. And I can see if I do the math, they were doing it from 26 to 10. So that difference is going to be 16. So that's going to give me 144 meters during that window. And then the third one, maybe I'll be fancy and change to green. It's a constant again, but now it's a constant deceleration. So the 2 numbers would be 9 plus 0 divided by 2. So that gives me 4.5 meters per second times, this time it's going to go from 26 to 38. So that's going to be for 12 seconds. So that's going to give me a distance of 54. So I've gone in total 253 meters. So if they ask us to calculate the average speed of the car, they tell us here the average speed is going to be total distance, which we said was 253 meters. And the total time is 38 seconds. So your average velocity is 6.7 meters per second. Again, this is all average, so it's not the calculus stuff, it's just the
Mhm.
average. So this would be, if you had the curve, it would be the slope of the secant line. So then we come a little closer to calculus. So here's Craig's 3-hour bicycle ride. So we have his time in hours and how many miles he's going. Okay, so to figure out his instantaneous velocity, they want to know whether it is positive, negative, or zero. So what we're going to do is we're going to draw a tangent line to the curve at that spot. So at 0.5 hours, that's point A. So if you were going to draw a tangent line, that gives you the instantaneous speed as opposed to the average. And you can see that it's going to be positive. I don't know what it is. If I, extended it and kind of figured it out, I could figure it out, but I can clearly see it's positive. And then the next point they want us to look at is right here. And that you can clearly see is 0. So the velocity is 0 there. And then the next point is at 2 hours, which is at C, and that's negative. So I have indications of what instantaneous velocity is. So it's not the average, it's right there at that point. So I'm now talking about the slope of a curve. And I approximate it by drawing a tangent line that touches that curve only one place, as opposed to a secant line, which gives me average and touches it in 2 places. Okay, so pick another place, another point besides A, B, or C, where Craig's instantaneous velocity is positive. So what number would you like?
1.
Me too. So I think 1 looks like it's going to go about with 8. So I would say the point coordinate pair is 1, 8. And I agree. Positive there as well. Okay, another place where it's negative.
2.5.
2.5 is a winner. So that looks like maybe 2.5, 2.510 maybe? Maybe we'll say 2.59 because I
Yeah.
up. Yeah.
Yeah, like 9.
9 works.
Mhm.
And then another point where it's 0. So you see another flat section? Right
I
at
mean,
that
stops
0.
at 3 hours, but I can't assume that. It kind of looks like just before 2.5 where it has that second hump, that could be
Right.
another 0.
Yeah, that's what I think too.
Mhm.
So let's say that that's 2.25.
Mhm.
Okay, good. So yeah, we stopped there, but we don't want to use that bottom number.
Yeah.
Okay, so this is all slope. And now we're kind of getting into the calculus of it. When did you take calculus last? Do you remember?
9 years ago, because yeah, 5 and then another 3. So 8 years ago. It's
Not
been a while.
bad. So is this sounding kind of familiar?
Yeah.
Yeah, it should go back. It should come back so we don't go that deeply into it.
Mhm.
But it is kind of neat the way they do it. It's such a visual thing first,
Mhm.
and then they kind of skip over the rules and just keep it visual. But I didn't want to do that. So I kind of add my own stuff to it. I thought this was neat. They use Desmos for everything. So I just took the Desmo pictures as well. So it says comparing average velocity with instantaneous. So the key is know that the red curve is your main curve. Okay, so that's we'll call it even your parent function. So that's a cubic. And what they did was they said, okay, I'm kind of looking at this 2.8, and I want to figure out both average velocity and instantaneous, but I'm going to do it all at once. And they present the answers in this way. So that is point slope form. And that's your classic form of a line in calculus. So looking at this, I can kind of figure out what the curves are. The colors tell me too. But the green curve is where we are tangent to the red curve. So the green curve is a tangent line. And tangent lines give us instantaneous slope or instantaneous velocity. So this is your instantaneous velocity. So that's the velocity right at that point being 2.8. Whereas the blue line, this blue, they took the secant line and they figured out what is the slope of this line between those 2 points. And so that's going to be your average velocity. So you can see that if you were just dealing with average velocity, you wouldn't appreciate how fast it's moving at the 0.28. Instantaneous is 3 times as fast. But that's how they relate the two. Then they tie that into this idea of limits. So the official definition of a limit is this. And then they say, okay, we have a cubic function. So we want to figure out what is the equation of the slope. So they want this tangent line slope. So to get it, they took the theory and then they plugged in the actual function. And it's just the parent function not transformed in any way. So they are at this point, which basically is just change in y over change in x. Then they expand. And once they expand, they also said, oh, look what's happening. These guys cancel. And when you do this, the bottom line is any term that doesn't have an h attached to it will cancel. If that doesn't happen, go back and figure out what's happening here. Because you shouldn't have any terms left that don't have an h attached to it. So then if you factor out the h, at this point when you can cancel, then you can actually take the limit. And so these become zeros, and that equals your slope. And this slope is very x dependent. So it will give you the slope at any point along that function. So that's the nicety of slope. So we're going to do these limit equations in the problem set coming up.
Okay.
So then they said, okay, let's go back to a simpler curve. And they said, why don't we see if you can guess what the slope would be? So they give us a plain old parabola. And then they said, okay, sketch tangent lines to the 3 points drawn to the parent function. So here's one of them right here. So you want to hit it so that it's just going one place. So if I do it really well, let me just go back. If I can do it really well, I can actually get 2 good points. And then I can calculate the slope of that line, which is going to be 2 over 1 or 2. And if I did the same thing here and I hit that nicely, then I can calculate the slope of that line, which would be a negative 2 over 1. And then the third point is where it's horizontal, which is down here, which I know nothing changes, so the slope has to be 0 there. So I'm getting my values, and now can I prove that using my math? So we could race, let's see, we did that. Okay, so you want to find the derivative of all these places. So are you rusty?
Yes. Oh my God.
I know, it's awful. So this is how you start out, okay? So the limit as h goes to 0, and then you would say, take my function and add h to it, and then subtract this. So this is your theoretical setup. And then you have this minus this. Now you say, okay, that's not my real function. Let's do it for real. I'm still doing the limit as h goes to 0, but now I'm going to say my function is x plus h squared minus f of x. And then a plus h minus, well, I'm going to change that to x. Let me go back. Okay, x plus h minus x. Okay, so now we're getting serious. So when we do the next step, we're still writing limit because we can't take it yet because we're going to have a 0 in the denominator. So when you expand and you actually plug in, you're going to get x squared. Hang on. So I'm in the, yeah, I'm in this page. X squared plus, that's going to be 2xh plus h squared. Okay, that's the whole function with the h attached. And then minus, here's where you're going to be canceling. Then I'm going to cancel in red my little x's and put my little h here in green. Okay, so now I can cancel also in red these guys. Once I cancel those guys, now I'm ready for the next step, because I can say the limit as h goes to 0, factor out that h. Because now everything is nice and clean. And that's going to give me 2x plus h. Even though you have an h in here, it's okay, because it's going to go to 0 anyway. The most important thing is that you need to have these two h's to cancel. So once those two guys cancel, then what we know is that we can now call that to the derivative, because we're going to take the limit, plug in the 0, and you're going to get 2x.
Oh.
But so you don't drop the notation limit as h goes to 0 until you're able to cancel the h. Otherwise, you have an undefined term. Isn't that beautiful how it works out?
Yeah.
So then we can compare what we found up here, because now we see that our slope is x dependent. And if my x was 1, which it was in the first case, then my slope would be 2 times 1, which would be 2, which is what we got when we actually did the slope. Same thing for 0. So when I plug this in, so what I'm doing now is this. I'm going to evaluate the slope when x is 1, and I get 2 times 1, or 2, and that verifies with my curve. Plug in your 0, that's going to give you 2 times 0, or 0, which is when the slope was in the middle there, when it was flat. And then the last one, when you evaluate it, you get -2. So it all works out. So when you take a parabola, you can find every slope by just plugging in the x value to this expression. And then this next one, they did limit a different way. They talked about it mathematically. So they show you this crazy curve, and they say, we want to find the limit as x, as your a approaches 3 from the right and from the left. So here is your 3. So we want to approach here. So what they're going to do is they're going to say, okay, let's approach from the right. So they would plug in numbers, and they would get really, really close to adding a 0, because it's the same idea as limit. Okay, so this is your equation. And they're going to try to plug it in from the left and from the right. So first they say, okay, what if h is 1? So if h is 1, this becomes -1. What is if h is 0.1? Then we have another number. We know that if you can't put h at 0, right? Because then you're undefined. So we're doing it as it approaches. So you're approaching so closely, and I'm going down into very small numbers here. Then approach from the other side. So what if your h was -1 and you're trying to approach and get closer and closer? So you start out that's still going to be a 1. This is going to be like a 0.5421, 0.4640, 0.4557 if I do all the math. And this is 0.4549. So you can see whether you're approaching from the right or the left, the limit is the same. And that's what we want to have. If you have the same limit on either side, then you can say the limit does exist. And so what's the limit? So the derivative of the curve at h is that limit, at x equals 3 is that limit. So it's approximately 0.45. And the fact that it's the same from the left and the right, you can say the limit exists. So there's no holes, there's no like funky things going on, there's no points happening. So that's the other approach to limits, is you're coming from the right and from the left. So then now we kind of do some fun stuff. We say, okay, what if your first function was a cubic? So the first function is a cubic. So that's the green. So let's just say that this is some cubic function. What you end up learning over time is that if your first function was a cubic and you take the derivative and you plot it, that second function will be one step down. So it won't be x cubed, it will be x squared. So that's going to be a quadratic. And then your next derivative will be one step down from a quadratic, which will be a line. So I think that's always kind of a cool thing. So if this is, I'm going to say, we'll use the notation. If this is my f of x, then this is my f prime of x, and this is my f prime prime of x. So there's some analysis we can do here as well. So if you look at the cubic, and the cubic's some kind of dark color, key points are where that cubic is 0. So if you mark where it's 0, and then you look straight down, you will see the roots of the quadratic. So it just so happens for this one, everything is kind of interacting right here, but the one on the right is a lot clearer. The other thing that's happening is you have an inflection point, and an inflection point is the most steep part between the low and the high. So it is basically somewhere in here, and you can see where it is because that steepest part will be the max right here of your quadratic. So that's another feature that lets us identify why the cubic and the quadratic are related. So then you can go the same way and you can say, okay, let me look at the first derivative, which is the red, and I can say, all right, where that has a flat top where it reaches its max, the slope is 0, therefore the derivative, which is the line, is going to have a root right there, and that root is directly below. Then what you can also say is, let's look at the slope to the left of that max. The slope is positive there, so you would read positive values off of your second derivative, and that lines up. Once you go past the max, then your slope is going to be negative, and that slope is reflected by the negative y values you would read on that side of the line. Is this coming rushing back to you?
A little bit.
Good, good. Okay, so look at these. So if you try to hand sketch, when you do the first one and the third one, that slope is a constant number. No big deal. Can you try to do the second derivative or the first derivative of that function? So if this is your original function, so this first derivative would be a number greater than 0, right? Because it'd be a positive slope. this first derivative would just be a number less than 0 because it's a negative slope. But this one's going to be an actual interesting function as opposed to just a point. So can you use your landmarks to see if you can get the first derivative?
Do my best.
I'm going to do it also. So look up if you need support.
Okay.
So that's what I'm getting. What do you think? Get your landmarks. So get your tops and your bottoms. Those have got to be the roots, right?
Yeah.
Okay, so then in between your high and your low, figure out where the inflection point is. It's probably there. Since that slope is negative, that's going to be a minimum on your first derivative.
Okay.
Then do the same thing between your low and your high. Figure right around here. That's going to be an inflection point. That's going to be positive, but it's not as big. It's not as positive as the other side is negative. So I made it a little bit lower. And then I just play connect the dots.
So it's like a rough estimate, right? Like I won't know for sure like where the true minimum on the green graph is or
exactly.
the max. Okay, it's
What
just
you
a
do
rough
know
idea.
for sure are the roots.
Okay, okay.
And then we're just approximating. So that's your first derivative.
Okay.
Okay, let's see if we can get the next one. So same idea, take your green curve and figure that's going to be a root, and that's going to be a root. Now that's a cubic, so this is going to be a quadratic. And then say if this is the inflection point, the slope is positive there. So it's going to be somewhere up here. And so I would get a shape like that. So that could be my f prime prime of x. And then it's easy. So if that's your parabola, then here is your max. And to the left of it, the slope is negative, and to the right, it's positive. So your line is going to go straight through that point. And that would be your fourth derivative. Your fifth would be a positive number because it would just be the slope of that line. So that's kind of cool stuff. And then
That
if you
makes
wanted
sense.
to talk about limit with it, I think I liked using just the derivative, sketch the derivative by hand, because that is very cool. So the derivative for the first one and the third one would be just a constant, and it would be one value, and it would always be the same because it's just a line. And the slope of a line is always the same. Okay, so then they do some more of this, and they give you some more notation. So I've been using f prime of x as a derivative, but another way to do it is to call it dy dx. And then you can also do this. When I took a derivative at a certain x value, I wrote that, but you can also write this. So it's kind of like the word ice in the Eskimo language. It's important, so there's lots of ways to say it. Same thing for derivative, lots of ways to say it. And then the third notation is this. This is a command. It tells you to take the derivative of f of x. So that's a little fun fact there. So let's see what we're doing here. Here they give us a function. Okay, so that's a function. And why don't we figure out the maxes and the mins? So here's a max. Here's a min. And then someplace in between is going to be the inflection point. And we can figure out where that is on the next one. So this is just giving you this function. They took the derivative, but they didn't write it. They didn't post it until here. So you can see that now they're telling you how far down that inflection point goes. Because remember, that's what we were approximating for the other one.
Mm-hmm.
So here's your max. Here's your min. So what we should be seeing is they turn into the zeros of your second function. And that worked out. And then, so then this right about here must be the inflection point. And you can see the slope is negative, so that's why it's a minimum of the first derivative. So here is your, I'll use the right colors. Here is your initial function. And then here is your first derivative. Then they go on. So for the second derivative, they do it on the next page. So here it is. So here's all of them at once. So your original function was the green. So this was your f of x. Then this is your f prime of x. And then the line is going to be your f prime prime of x. Okay, then they talk about concavity. So let's first analyze this a little bit. So I did the original function in the first derivative. Does the second derivative make sense to you?
Mm-hmm.
Does that second derivative, is that okay?
Yeah.
This is your min, right? So I'm here. This is going to be a 0 of my second derivative. And then it's going to be a positive slope because the slope values go from negative here to positive here. So I'm reading off negative values down here, reading off positive values down up here. Okay, so that's good. Okay, concavity. So concavity is changes at the inflection point. So clearly, like right here is going to be our inflection point, right? So if I go straight up, so here's my inflection point. So on the left side, so let me use my little highlighter. Here to here, the function is concave down. So we are concave down in the yellow. So let me highlight that in yellow too. As opposed to, let me go to green. Here to here, we are concave up. And the dividing line is the inflection point. So the cubic has two kinds of concavities, and it has one inflection point. The quadratic, which is the first derivative, doesn't have an inflection point. And so it only has one kind of concavity, and it is always concave up. So this guy is always concave up. If it was going the other way, it would be concave down. So know that the point of inflection, I think it says that in here. That is really important. The point of inflection is what is the dividing line between the concavities. And remember, the inflection point is the steepest point of the curve, and you find it between the max and the min, or the min and the max, depending on where you're looking.
Mhm.
And that's where that is. And the inflection point of the original function will either be the minimum or the maximum of the first derivative. And it'll be a root of the second derivative. Then they talked about, can we figure this stuff out without actually drawing the other curves? Well, I kind of drew the other curves anyway. They want to know, so and the textbook does this as well. What is the slope of the different points for the first derivative, the second derivative, and the original function, the first derivative, and the second derivative? So if you look at A, so I see that A has a positive slope right here. That makes sense. So why don't we try to draw in the other ones, and that will help. So I'm going to use blue to draw in this guy. So I know that this has to be a root, right? This has to be a root. And then this inflection point is at C. It's a positive slope. So this is where I'm kind of guessing. I'm just going to put it there. So that would be my first derivative. So this was my original function. And then based on that, I could do another derivative. Here is where it's 0. And if I look to the left of that point, my slope is positive. So that means that my line would go like this. And that would be my second derivative. So when they say these different points, they're really asking for the x values. What's the slope at that x value? So if this is your A point, then that would be down here. The same x would be down here. And I would have a positive slope there. So let's see, at A, wait 1 second. So at A, oh, in the original, okay, I got, well, let me see. I have to think about this now. At point A, f of x is a positive value. Yes, it's a positive value, right? That's a positive value. F prime of x would be where? It would be all the way down here. So you would be reading negative values because that's the slope at that point. That's why that's a negative. Then your next one, your f prime prime of x, that's going to be up here. That's going to be a positive value. So you're read off the y-axis. So we're reading off y for all of these. Okay, so your b right here on the original function is going to be 0. But your b down here, well, I take that back. Let me not interpret it that way. Your b right here is a positive number. But here, the b you're going to read that's associated with that is going to be a 0.
Mhm.
And above that will be a positive for your line. And then c is a positive number. C on the first derivative is also positive. C on the second derivative is going to be 0. D, you're going to read off the y-axis, it's going to be positive. But then if you read down, that should be a 0 there. And then it should be negative over here. And the last one, E, you're reading a positive y value. And when you read way down, they both will be negative.
Mhm.
So you're looking at the x values here. But then these are all y values. So they did a lot of like playing around with this stuff without any formulas or anything. So I do kind of think that's a neat way to do it.
Mhm.
Why don't we try to do one more derivative, one more limit so that you get really comfortable.
Good.
So what if I said my function was just x squared plus 2? And you need to find the limit as h goes to 0. So you would start off with let me back up. So put the h right in next to that.
Mhm.
And then you're going to subtract away. Now, you probably want to use parens. And then down below is always going to be x plus h minus x. And then distribute. Okay, I need one more letter in there. I need a 2 in here. So then this is still plus 2. Okay, so this is that's why it's easy to catch your mistakes. These have to go because they don't have an h attached to it.
Mhm.
And then these have to go because they don't have an h attached to it.
Yeah.
And then these can go because I don't need them any longer. So then your next thing is going to be to now make it simpler. So I have just this. And I'm still taking the limit as h goes to 0. And at this point, when things I can factor out, so I'm going to do it one more time. Factor out that. And then once you cancel it, then you can say the limit as h goes to 0 is going to equal, and that's going to be f prime of x at this point, 2x.
2x. Yep.
Done. Okay, good. And then, when we do the rules of taking derivatives, you can directly say, oh yeah, that derivative is just going to be 2x because of the power rule.
Mhm.
But we'll do that another day. But right now you have to be able to do it with the limits.
So I actually didn't learn like this way. Like I learned just like the power rules. So I actually really liked seeing this because I was always like, where did those rules come from? Why do I
Oh,
do it?
gosh.
Okay, shut
Oh,
up and do math.
yeah.
Okay.
Yeah, so what's nice, if you know the power rule, you can always check your work.
Yes.
If you know what you're getting to, but that's how you do it. Yeah, it's
Mhm.
kind of a cool thing.
Mhm.
Yeah, when I teach it, my kids don't know the power rule. So they have to just really be careful about the algebra. And that's
Mhm.
really good practice for them. So it works out. But I like all the curves. And it is really good to have an understanding of how one curve impacts the other curve.
Mhm.
Oh, and I should say too, a lot of times you use this in terms of like a physics class. So your first function would be like a position function, like that car that we talked about.
Mhm.
And then your second function, f prime of x, would be velocity. And then your third function, your third derivative, or your derivative, your second derivative, the third function would be acceleration. So given a function, you can use calculus to figure out an equation for your acceleration at different x's. So that's kind of cool. So that works out well. But in terms of just knowing the curves and how one reflects the other is nice, because you can, if you were going to sketch it, you have to go with your landmarks. And so you can easily figure out if you made a mistake someplace. And it just helps, I think, with the understanding of it. So that's the entire lesson today.
Wow.
So if I had two of you here, I would like do some more practice back and forth. But that was a lot of writing, a lot of stuff.
Mhm.
So what do you think about all of that?
I did have a question about the initial derivative equation where in the denominator it's a plus h minus a. What's the point of having that if the a's or the x's that they become are just going to cancel?
Good questions. Let me get where I have something like that set up.
Mhm.
Okay, so your numerator is change in y,
Mhm.
right? Your denominator is change in x. So aren't you adding h to it and then subtracting it? So it's x2 minus x1. This is your x2 which has a little h with it. And this is your x1. This is your y2 that includes the h,
Oh.
and this is your y1.
Oh, that makes so much more sense.
Yes. So that's why you have it. So yes, it does cancel out. And a lot of teachers will just not even tell you that. They'll just say
That
just
makes so
divide by
much more
h.
sense. Oh my god.
Yeah, that's what it is. So it truly is a slope equation.
Oh my god, that's awesome.
So it all makes sense.
It just clicked. Oh my god.
But that's exactly why I always have my kids do this step first. Like, don't just tell me to divide by h, because I want you to see that it is
Mhm.
just change in y of a change in x. So you need to have y2, which has an h with it, y1, which is your original function, original parent function, and then x2 minus x1. And the whole thing is, to the other thing, you can't take this limit because you can't plug in a zero in the denominator. So you have
Mhm.
to keep waiting and waiting and waiting, and you have to write it over and over again until they cancel. And then once they cancel, you're actually taking the limit.
Mhm. Yeah, because h is just 0.
Right, right. Yeah, but you can't take it until you have them cancel. So that's
Mhm.
why you have to make sure that you can cancel between the numerator and the denominator, the h. So if you've made an algebraic mistake someplace and you have like this extra number over there, then you can't cancel it. So
Mhm.
that's why it's a really good algebra review. And my kids usually tend to be better at calculus than they are at algebra. So it's a good review.
Oh, yeah.
So in the problem set, I have you do a lot of these. So look at that, make sure that that seems okay. And then what
I
I'll
don't see
do
it in
is,
there. The
what's that?
problem set, it's not published.
Oh, okay, so I'll make sure that's published.
Mhm.
Because I have to go in and do that. So I will do that. And then what I'll also do is I'll put up the video for this, and I'll probably put up the filled in notes as well. So you'll have
Perfect.
everything up there.
Cool.
And then just get a journal article, follow the rubric, and just post that the way you posted this previous assignment. And
Okay.
then I'll post so when I post things, when I publish things, you'll have a place to plug them in too to submit them.
Mhm.
Okay, good, good, good. So if you ever have a conflict, just let me know. And I can kind of do this for you as well, so that we
Okay.
have, coverage, because I can do the lesson this way and then post it. It's a little bit easier if everyone's here because
Yeah, then you have to
for our
record
questions.
anything, yeah.
And this is a lot, so hopefully Sarah has a little, Catlin has a little background in calculus as well,
Mhm.
because it's a lot. The book goes through it as well, but so see what you think. So you
Okay,
get an early out today,
cool.
which is good. So I'll stop sharing this and then I'll stop the video. And then as you look at the problem set, once you see it, if there's any issues, just email me.
Okay, cool.
Okay, and then we'll be good. So very good. We'll have a lovely evening, and then I'll have
Yeah,
all
you
the
too.
stuff up for you later on tonight.
All right, cool. See ya.
See ya.